Greetings, everyone. Let's talk some of the problems from section 2.6. There's some of you who are asking about problem number one, and problem number one is supposed to be a really basic problem, so I don't, maybe it's just too simple and you guys are overthinking it, or more than likely, I just think you guys need to go back and reread your notes a little bit. The curve has equation y equals f of x, right? An expression for the slope of the secant line through the points P and Q. P is 3 comma f of 3 and Q is x comma f of x. It's the slope of a secant line, ladies and gentlemen. It's just change in y over change in x. So your expression, just subtract the y values, put that in the numerator, subtract the x values, put those in the denominator. That's it. And this is in your notes at the start of this section, because I drew some pictures and I wrote out how to find the slope. Right, and part B, write an expression of the slope of the tangent line. The tangent line is just the slope of the secant line with a limit. Okay, we're going to let the limit as x goes to 3 for your answer to part A. I'm not going to write anything down. You should go back and search for that stuff in your notes. It's not that hard to find. And I think I used A instead of X in the notes, but that's not going to change anything significantly. The next question that we need to talk about is number 10. And number 10 says to find the slope of the tangent line, or the tangent to the curve, y equals 1 over root x at the point where x equals a. All right, so, oops, I need to get over to the screen right here. And so we're going to find the limit as h approaches 0, f of a plus h minus f of a over h. And then we'll actually apply it to this particular function. And so we're going to get 1 over root a plus h minus 1 over root a over h. Now, the first thing I would do here is I would do the algebra to find a single fraction, or combine the fractions in the numerator here into a single fraction. And when I do that, my common denominator is going to be the product of root a plus h times root a. Now, technically, this is all still over h for this h that's down here, but remember, that means that h just becomes a factor of the denominator, something else we talked about in our notes already. And then over here, I need to multiply this numerator on the left by root a, and then this numerator on the right by root a plus h. So we get this. And then from here, we're going to rationalize. Whoops, get the order right here, excuse me. Root a plus h over root a plus root a plus h. I'm not going to help too much more. I'll do a little bit of the algebra, and then I'll kind of let you finish it. So remember, we get a difference of squares pattern up here, so we're going to get a minus the quantity a plus h. Those parentheses are important because you need to distribute the subtraction there. Don't distribute in the denominator, as I've advocated many times. So once you cancel the a's from the numerator, a minus a, you'll be left with a negative h. You'll cancel the negative h with this h here, leaving just a negative 1 in the numerator. And then from there, just let the two h's that are left in the denominator become 0, as the limit says, and then you'll have your expression for the slope at a. Now for B, it says to find equations of the tangent line. So not just slopes, find the equations of the tangent lines at 1, 1 and 4, 1/2. So to write the equation of a line, remember, you just need the slope and a point. Well, they gave you the point. So take the 1 here, plug it in to your answer after you simplify here for A. Hopefully the neighbor's gardener's far enough away. It looks like he's coming back, but you're going to plug 1 in for A into your answer here after you simplify. That'll give you the slope, and then you have the point. Similarly, you'll plug 4 into your expression for A, then you'll have the slope, and then you'll have this point, and then you can write the equations of those tangent lines. And then it says to graph the curve and both tangent lines on a common screen. Just go to Desmos, type in, 1 over x is your function, type in your two equations for the two tangent lines, and go take a look at them. That's what they want you to do on that one. The next thing we have is number 11. And it says a particle starts by moving to the right along a horizontal line. The graph of its position function is shown. When is the particle moving to the right, moving to the left, and standing still? Draw a graph of the velocity function. Well, the moving to the right part, well, if this, as it says here, a particle starts moving right along the horizontal line. So it's moving horizontally here. It's not moving along this diagonal. It's not moving then this way, moving this way. This just tells you how far it is at any given time from the starting point. It's just moving back and forth. This is its position function. So it starts at the origin, okay? And then after 1 second, it's 3 units to the right, okay? Well, if it starts at 0 and then moves 3 units to the right, from 0 to 1, it has to be moving to the right, okay? And then from 1 to 2, it's still at 3. It's not moving anymore. It's standing still during that point. And then from 2 to 3, it was at 3 units to the right, and now it's only at 1 unit to the right. So it had to be moving to the left because the distance got smaller, got closer to where it started. And then from 3 to 4, it's still 1 unit, so it's not moving anymore. And then it starts to get further away again and get again back to 3. So that's how that should look. Now, how does the graph of the velocity function look? Well, from here to here, from 0 to 1, the graph, the velocity function, I'm thinking position, the graph of the velocity function, from 0 to 1, remember, the velocity is the slope of the tangent line to the graph of the position function. So the slope of this line here is the value of the velocity function. So the slope of this line is 3. So from 0 to 1, the velocity function is 3 the entire time. Then on the next little interval, the slope of this line, which is 0, that's going to be your velocity function. So first you'll have a horizontal segment from 0 to 1 at 3, and then you'll have a horizontal segment from 1 to 2 at 0, and then just keep doing that. This one has a negative slope, so from 2 to 3, your graph will be somewhere down here, but you calculate the slope. Then it'll be back to 0, and then it'll back to being positive. Okay, and then you can sketch those. So basically, for this picture, the velocity function is a bunch of horizontal line segments. Let's squeeze one more into this video if we can. Number 12, shown are graphs of the position function of two runners, A and B, who run a 100-meter race and finish in a tie. Looks like we have to go over to the next page for the questions. Describe and compare how the runners race. At what time is the distance between the runners greatest? What time do they have the same velocity? Okay, so describe how they compare. Distance between them is the greatest, and same velocity. All right, there we go. Well, runner A is running at a constant rate. Okay, this is its position function, so the slope of that line is the velocity function, and since this is a line, the slope is always the same, so he's running at a constant rate the entire time. Runner B, however, if you imagine a tangent line along here, the tangent line is not very steep at the beginning, gets steeper and steeper and steeper and steeper and steeper, so it starts off slower and increases speed. Okay, they start in the same place here. They end in the same place here. That's why the outputs are the same. The distance between them, this is a vertical line between the graphs. So at 2 seconds right here, how far apart this little line segment is right here, okay? That little line segment, that's how far apart they are. And then over here, that's how far apart they are. So what you have to do is you have to figure out when is the vertical line between the two graphs longest. That's when they're furthest apart. I'm not going to give you an answer for that. I want you to just kind of do your best to approximate that. Okay. And then when are they traveling at the same speed? Well, remember, the tangent line gives you the velocity, and the absolute value of the velocity is the same speed. And if they ask for velocity, then the absolute value doesn't matter. In this case, it's not going to matter anyways because they're both going to be positive anyway. But so it's the slope of this line here. If I can imagine the tangent line to B, I want the tangent line to the graph of B to be parallel to this line for A, because then the slope of that tangent line would have the same slope of this line, which means they'd have the same velocity, and in this case, the same speed. Okay, so again, you're going to have to approximate at what time, so along here. So just imagine drawing in some tangent lines along the curve, find one that's parallel, or if you could imagine picking this up and dragging it over so it stays with the same slope, but until it just is about to not touch B any longer, then at that point of tangency, just look down and see where it's touching the x-axis, or where it would be touching on the x-axis, and that'll be the value of t at which this happens. Okay, so that's what you need for that one. All right, more videos to follow.